4 days ago, 4 astronauts came home from the moon. They might be the last ones who do, not because something goes wrong, not because a rocket fails, but because NASA isn't building a program that brings people back anymore. So what are they actually building up there? A program that keeps them. Nuclear reactors buried under regolith. Fuel made from ice that arrived before life existed on Earth. Construction crews, safety zones, crew rotations without return dates printed on them. Artemis 2 wasn't a homecoming. It was the final dress rehearsal before a door opens that doesn't close again. The next humans who reach the lunar surface aren't going to visit. They're going to work and build and stay. And somewhere in the next 20 years, a human being is going to die on the moon, not from disaster, but from old age, in a bed, under a roof that was 3D printed out of moon dust. That is the moment the moon stops being a destination and becomes a place humans belong to. If you're new here, subscribe and get comfortable, because tonight I'm going to show you how your quiet little neighbour in the sky just became the hottest piece of real estate in the solar system, who's racing to claim it, what's already being buried under its surface, and why the people alive right now are the last generation who will ever look up at a moon with no one living on it. Now, settle in and let's ease into it. Part 1. The splashdown that lied. 4 days ago, 4 human beings fell out of the sky at 25,000 miles per hour, and the world celebrated a homecoming. But what if it wasn't one? On April 10th, 2026, at approximately 12:17 Pacific time, the Orion capsule punched through the upper atmosphere trailing a sheath of superheated plasma that reached temperatures north of 5,000 degrees Fahrenheit. That's roughly the surface temperature of the Sun. For about 6 minutes during that descent, the crew of Artemis 2 disappeared. Not metaphorically, not dramatically, but literally. The plasma wrapped around the capsule so completely that no radio signal could get in or out. Mission control in Houston went quiet. The tracking stations went quiet. 4 human beings were falling toward the Pacific Ocean inside a fireball, and for 360 seconds, no one on Earth could confirm they were alive. Then the parachutes opened. 3 massive red and white canopies bloomed against the California coast sky, and the capsule drifted the final few thousand feet into the ocean, with the lazy calm of something that hadn't just survived re-entry from lunar space. Recovery divers were in the water within minutes. Helicopters circled, cameras rolled, and when the hatch finally opened and all 4 astronauts stepped out under their own power, upright, conscious, smiling, the narrative wrote itself before anyone had time to question it. "We're back," the headline said. "America returns to the moon." 54 years after Apollo 17's crew left the lunar surface for the last time in December of 1972, human beings had once again travelled to the moon and come home. It felt like closure. It felt like a circle finally completing. But here's the thing no one is saying out loud. This wasn't the end of anything. The splashdown of Artemis 2 wasn't the finale of a program. It was the starting gun. And the race it kicked off isn't the one most people think they're watching. Because while the networks were replaying that parachute footage and interviewing the crew about what it felt like to see the far side of the moon, something was already happening 400 miles inland. At the Kennedy Space Center in Florida, inside the Vehicle Assembly Building, a structure so large it generates its own weather patterns, technicians were already stacking the next rocket. Not planning it, not designing it, stacking it. Bolting together the segments of the solid rocket boosters that will power the next Artemis mission. A mission with an entirely different purpose than the one that just ended. And that's the detail that should make you pause. NASA is not consolidating. They are not slowing down to savour the victory. They are accelerating. The cadence they've laid out, Artemis 3 in 2027, Artemis 4 in 2028, Artemis 5 potentially months after that, is not the rhythm of an agency revisiting old glories. It's the rhythm of an agency building something. Something that, once operational, changes what the moon is. Not a destination, not a place you visit and leave, something else entirely. Think about what a normal victory lap looks like. After Apollo 11 landed in 1969, there was a global parade, ticker tape, congressional hearings, magazine covers for months. The Apollo program continued, yes, but the emotional arc was clear. We went, we won, we came home. The moon was a trophy. You don't move into a trophy. Artemis doesn't have that shape. The emotional arc of Artemis bends in only one direction, and that direction is forward. Every mission in the manifest is more complex than the last. Every mission stays longer. Every mission brings more hardware. And critically, every mission depends on the one before it in a way that Apollo never did. Apollo missions were largely independent. Each one could have been the last. Artemis missions are chapters, and chapters don't exist without a book. So what's the book? That's what this video is actually about. Not the splashdown, not the celebration, not the 10 days that Artemis 2 spent in space validating systems and breaking records. Those things happened, and they mattered, and we'll get into every detail. But they mattered for a reason most people haven't fully processed yet. The systems that Artemis 2 validated, life support, navigation, thermal protection, deep space communications, those aren't tourism systems. You don't need a closed-loop life support architecture to visit somewhere for a weekend. You don't need to prove that a heat shield can survive multiple re-entry profiles unless you're planning to use it over and over again. You don't stress test a communications relay during a 6-minute blackout unless you're building a world where blackouts are a regular operational hazard, not a one-time drama. Everything Artemis 2 proved was a prerequisite, not for going back, but for staying. And here's where the quiet part gets loud. The next humans who reach the lunar surface, and they will reach it, probably within the next 2 years, are not going there to collect rocks and plant flags and come home to ticker tape. They're going there to begin building a permanent human presence on another world. A presence with power systems, resource extraction infrastructure, habitation modules, legal frameworks, and crew rotations that stretch from weeks to months to, eventually, something that doesn't have a return date printed on it. The last humans who came back from the moon may already have landed. They splashed down 4 days ago in the Pacific Ocean, and the world cheered because it looked like an ending. It wasn't. Part 2. The 10 days that quietly changed everything. To understand what Artemis 2 actually accomplished, you need to forget the splashdown, forget the parachutes and the recovery ship and the smiling astronauts. Rewind 10 days and start at the beginning, because the mission that just ended wasn't a trip to the moon. It was something far more calculated than that. On April 1st, 2026, 4 astronauts launched from Kennedy Space Center aboard the Space Launch System, the most powerful rocket NASA has ever built, generating 8.8 million pounds of thrust at liftoff. That's roughly 30% more power than the Saturn V that sent Apollo to the moon. Within minutes, they were in low Earth orbit, moving at approximately 17,500 miles per hour, circling the planet while ground teams verified every system on the spacecraft before committing to the next step. That next step has a name that sounds almost mundane: translunar injection. It's a single engine burn that accelerates the spacecraft from orbital velocity to escape velocity, the speed needed to break free of Earth's gravitational hold and coast toward the moon. It's a one-way door. Once you perform that burn, you're committed. There's no easy U-turn from 250,000 miles out. And for the next several days, the crew of Artemis 2 did something that no human being had done in over half a century. They left the neighborhood. They crossed the radiation belts, passed through the void between Earth and Moon where there is no atmosphere, no magnetic shielding, no safety net, just vacuum and sunlight, and the slow realization that the blue marble behind you is getting smaller by the hour. The trajectory carried them around the far side of the moon at an altitude of approximately 4,700 miles. That might sound like a lot, but for context, commercial airliners cruise at about 6 miles up. The International Space Station orbits at roughly 250 miles. 4,700 miles above the lunar surface is close enough to see individual craters with the naked eye, close enough to feel the gravitational tug of a world with 1/6 Earth's gravity pulling at the spacecraft. and then they kept going. At their farthest point from Earth, the Artemis II crew reached a distance of 252,756 miles. That number matters because it broke a record that had stood since April of 1970, the record set by the crew of Apollo 13, who reached 248,655 miles from Earth during their emergency flyby. Apollo 13 broke that record by accident, because their spacecraft was crippled and they had no choice but to swing wide around the moon on a free return trajectory. Artemis II broke it on purpose, by design, because the mission profile required them to go farther in order to test the systems that future crews will depend on. And there's that word again, future. Everything about this mission pointed forward. During the far side flyby, something happened that no human eye has ever witnessed. The moon passed directly between the spacecraft and the sun, creating a total solar eclipse as seen from beyond the moon itself. For approximately 54 minutes, the crew watched the sun disappear behind the lunar disk, replaced by a ring of light, the corona, visible in a way that no earthbound observer has ever experienced. No atmosphere to distort it, no clouds, no horizon glow, just the raw physics of one celestial body blocking another, observed from a vantage point that only 4 people in the history of our species have ever occupied. It's tempting to dwell on the poetry of that moment, and we should, briefly, because it's worth acknowledging what it does to a human being to see the Earth reduced to a pale dot while standing in the shadow of the moon. Every astronaut who has travelled beyond low Earth orbit has described a cognitive shift, a sudden, visceral understanding that the planet you came from is small, fragile, and far away. The overview effect, psychologists call it. It changes people, it reorders priorities. But here's what matters more than the poetry. The reason those 4 astronauts were out there wasn't to have a spiritual experience. It was to prove that the systems keeping them alive could handle the environment they were in. And this is the part that gets underreported because it's not cinematic. It's not dramatic. It's plumbing and wiring and thermal management and radio frequencies. But it's the foundation of everything that comes next. The life support system aboard Orion is a closed-loop architecture, meaning it recycles air, manages carbon dioxide, regulates temperature and humidity, and processes waste without resupply. On the International Space Station, supplies arrive every few months aboard cargo ships. In lunar space, there are no cargo ships. What you launch with is what you have. For 10 days, that system ran continuously, and the data it generated, every temperature reading, every CO2 level, every filter cycle, feeds directly into the design of systems that will need to run not for 10 days, but for 30, then 60, then 6 months. Navigation in deep space was tested under real conditions for the first time with crew aboard. The star trackers, the inertial measurement units, the ground-based tracking network, all of it had to work in concert to keep the spacecraft on a trajectory accurate to within a few miles over a distance of 250,000 miles. A tiny error at translunar injection, a fraction of a degree, compounds over that distance into a miss of thousands of miles. The system performed. But performing once is not the same as performing reliably, and reliability is what you need when you're planning to send people back and forth on a regular schedule. The thermal protection system, the heat shield, was tested under conditions that approximated the fastest, hottest re-entry profile the capsule will ever face. Communications were tested through the blackout zone, through the latency delays that come with deep space distance, through the relay architecture that will eventually support a permanent communications link between Earth and the lunar surface. None of this is exploration in the way most people understand the word. This is validation. This is an engineering program methodically checking boxes on a list that leads to something much larger than a single mission. The European Service Module, built by the European Space Agency, the component that provided propulsion and power for the entire journey, logged approximately 700,000 miles of total travel. That module is the ancestor of the service modules that will support longer missions, more complex orbital maneuvers, and eventually, the logistics chain that keeps a lunar base supplied. What Artemis 2 proved, in 10 days of quiet, methodical work, is that human beings can survive in the environment between Earth and the Moon, not for a few hours, the way Gemini and early Apollo tested, not as a stunt, but as an operational reality, eating, sleeping, working, troubleshooting, maintaining equipment, and managing the psychological weight of being farther from home than any human being has been in 54 years. They didn't just go farther than Apollo, they stayed longer in the environment Apollo was designed to pass through as quickly as possible. Apollo was a sprint. Artemis 2 was the first shift of a long residency. But surviving and living are different things. The mission proved we can keep people alive away from Earth. It did not prove we can build a life there. That distinction between survival and habitation is the gap that every future Artemis mission is designed to close. And closing that gap starts with confronting something uncomfortable. The fact that the mission that just ended didn't go perfectly. Part 3. It worked, but not cleanly. There's a version of this story where Artemis 2 is a flawless triumph. 4 astronauts go to the Moon, come home safe, everything works, roll credits. And honestly, that version isn't wrong. The mission succeeded. Everyone survived. The spacecraft performed its primary objectives. By any reasonable standard, April 10, 2026 was a good day for human spaceflight. But reasonable standards aren't the ones that matter here. Because NASA isn't building a program that needs to work once. They're building a program that needs to work every time, for years, in an environment that punishes even small failures with catastrophic consequences. And by that standard, the standard of permanence, Artemis 2 revealed some cracks. Literal ones. Let's start with the heat shield. When the Orion capsule re-entered Earth's atmosphere at Mach 33, the UV-coat ablative heat shield did its job. It absorbed and deflected the thermal energy of re-entry, keeping the cabin temperature survivable, while the exterior was engulfed in plasma. But after splashdown, when recovery teams pulled the capsule from the water and inspected the shield, they found something that shouldn't have been there. Divots. Small craters in the ablative material. Cracks in sections that were supposed to erode smoothly and predictably. This wasn't new. The same type of damage had appeared after Artemis 1, the uncrewed test flight in 2022. NASA had studied it, adjusted the re-entry profile to reduce the stress on the shield using what they call a skip re-entry technique, where the capsule briefly dips into the atmosphere, skips back out like a stone on water, then re-enters again at a lower velocity, and the modification helped. The damage was less severe on Artemis 2 than on Artemis 1, but it was still there, and the mechanism causing it, the exact physics of why the ablative material was behaving unpredictably under real re-entry conditions was not fully understood. Computer simulations hadn't predicted this pattern. Ground testing hadn't reproduced it precisely. The heat shield works, but it works in a way that engineers can't completely model, which means they can't completely predict when it might not work. Now, for a single mission, this is manageable. You inspect the shield, you study the data, you refine the design for next time, but remember where this program is going. Artemis is planning for regular crew rotations, people launching to the Moon, spending weeks or months there, and returning. Every single one of those returns requires the heat shield to perform. If there's a failure mode hiding in the material behavior that only manifests under specific conditions that might not occur on every flight, then you have a time bomb built into your re-entry system, and you can't defuse a bomb you don't fully understand. Then there was the service module valve anomaly. During the mission, one of the valves in the European service module, the propulsion and power unit built by ESA, behaved outside expected parameters. The details NASA released were limited, but the implication was clear enough to require a redesign before the next mission. Valves in spacecraft are not decorative. They regulate fuel flow, pressurization, thermal management. A valve that doesn't perform precisely under every condition is a valve that could, under the wrong circumstances, end a mission. And then there was the toilet. It sounds trivial. It's not. The waste management system aboard Orion experienced a failure during the mission, the specific nature of which NASA described with characteristic understatement as a functionality issue. In a capsule roughly the interior volume of a large SUV, shared by 4 adults for 10 days, a non-functional waste system is not a minor inconvenience. It's a health hazard, a morale destroyer, and a design failure that becomes exponentially more serious as mission durations increase. Consider the scaling problem. Artemis 2 lasted 10 days. Artemis 4, the first landing mission, is projected to keep astronauts on or near the Moon for approximately 30 days. Future rotations at a permanent base could last 6 months or longer. A small leak on a weekend camping trip is an annoyance. A small leak on a 6-month polar expedition is a survival threat. Systems that can tolerate imperfection for 10 days cannot tolerate it for 180. There was also a communications asymmetry that emerged during the flight. At certain points, the crew could hear mission control clearly, but Houston couldn't fully receive the crew's transmissions. In an emergency, a medical crisis, a system failure, a moment requiring immediate coordinated action, that kind of one-way communication gap could be the difference between a save and a loss. And then there's the invisible threat, radiation. During the 10-day mission, the crew accumulated an estimated 12 millisieverts of radiation exposure. To put that in context, the average American absorbs about 3 millisieverts per year from natural background radiation. In 10 days, the Artemis 2 crew received 4 years' worth. The Earth's magnetic field, which shields the International Space Station and everything in low orbit, doesn't extend to the Moon. Out there, you're exposed to galactic cosmic rays and solar particle events, with nothing but the spacecraft hull between you and the radiation. 12 millisieverts in 10 days is within acceptable limits for a short mission, but extend that rate over a 30-day mission and you're at 36 millisieverts. Over 6 months you're approaching 200. NASA's career exposure limits exist for a reason. Prolonged radiation exposure increases cancer risk, damages the central nervous system, and may accelerate cardiovascular disease. Data from Apollo astronauts, who spent only days in deep space, showed a cardiovascular mortality rate of approximately 43%, compared to about 10% for astronauts who never left low Earth orbit. That's a small sample size, and correlation isn't causation, but it's a data point that should keep you awake. What all of this adds up to is a picture that's more complicated than the celebration suggested. The system works. Artemis 2 proved that. But working and being stable are not the same thing. A car that gets you to work every morning but occasionally makes a grinding noise you can't diagnose, that car works. You wouldn't drive it across the country. You certainly wouldn't bet your life on it for 6 months. And yet that's exactly what the program requires. NASA's approach is what they call iterative engineering, fly, learn, fix, fly again. It's the philosophy that built Apollo, that built the shuttle program, that built the space station. Keep moving forward, solve problems as they emerge, don't wait for perfection before taking the next step. There's wisdom in that approach. There's also risk. Independent analyses have suggested that the cumulative risk profile of the Artemis architecture, particularly the integration of new lander systems from SpaceX and Blue Origin that haven't yet flown with crew, may be higher than NASA's public assessments acknowledge. But NASA is moving forward anyway, and the reason has everything to do with what comes next. Because Artemis 3, 4 and 5 aren't repeat missions. They're an escalation, each one building on the last, each one adding another layer to an infrastructure that, once in place, transforms the Moon from a place humans visit into a place humans stay. The system works, but it's not stable, and NASA is building something that won't tolerate instability. What they're building starts with a mission that almost nobody understands correctly. Part 4. The mission that isn't a mission. If you ask most people what Artemis 3 is, they'll tell you it's the mission where humans land on the Moon again. The triumphant return. Boots on the surface for the first time since 1972. That's the story NASA's promotional materials suggest, and it's the story the media has largely adopted. There's just one problem. It's probably not going to happen that way. Artemis 3, currently targeted for 2027, is shaping up to be something much less cinematic and much more important than a landing. Based on the current state of development, the mission is more likely to be an orbital rehearsal, a test of the systems that make a landing possible without actually attempting one. The crew will launch aboard Orion, reach lunar orbit, and for the first time dock with the vehicles that will eventually carry humans to the surface. Those vehicles are the centerpiece of everything. SpaceX's Starship human landing system, a modified version of the Starship rocket, redesigned to descend from lunar orbit to the surface and back, is one. Blue Origin's Blue Moon lander is another. Both are being developed under NASA contracts worth billions of dollars, and neither has yet flown a crewed mission to the moon. On Artemis 3, astronauts will enter these vehicles for the first time in space. They'll test the docking interfaces, the mechanical and software connections that allow two spacecraft to link together in vacuum. They'll test the life support systems inside the landers. They'll test the propulsion systems that will need to perform a powered descent to the lunar surface on a future mission. This matters for the larger story because Artemis 3 is not about the moon at all. It's about infrastructure. It's about proving that the pieces of a permanent lunar transportation system can connect, function, and keep people alive. Without Artemis 3 succeeding, Artemis 4, the actual landing, cannot happen. And without Artemis 4, the entire architecture of permanence that this program is building collapses back into theory. Think of it like this. You don't build a house by starting with the roof. You pour the foundation first, and nobody photographs the foundation pour for the evening news. Artemis 3 is a foundation pour. It's the mission that makes everything after it possible. And it's the mission that history will largely forget, just like Apollo 9, the 1969 mission, where astronauts tested the lunar module in Earth orbit. The mission that proved the landing system worked before Apollo 11 ever attempted to land. Nobody remembers Apollo 9. Everyone remembers Apollo 11. But Apollo 11 doesn't happen without it. There's a hidden risk here that's worth acknowledging. NASA's Office of Inspector General has noted that the uncrewed demonstration flights of these landers may not fully represent the configuration that crews will actually fly in. That means the first truly integrated test of the lander system, with humans aboard, in lunar space, with all systems operating together, might happen on a mission where there's no backup lander, no rescue vehicle, and no ability to abort to a safe haven if something goes wrong. The crew will be relying on hardware that has never been tested in exactly this configuration with people inside it. That's the kind of risk you take when you're not just exploring. That's the kind of risk you take when you're building something, and the timeline matters, and the cost of delay is measured not just in dollars, but in strategic position. Because if Artemis 3 slips, if the landers aren't ready, if the docking systems fail, if the testing reveals a fundamental problem, then Artemis 4 slips. And every month Artemis 4 slips is a month that the window for establishing a permanent human presence at the lunar South Pole narrows. And the South Pole is where everything changes. Because Artemis 4 isn't going to the same moon that Apollo visited. Part 5. The landing that changes the destination. Every Apollo mission that touched the lunar surface landed near the equator. There were practical reasons for this. The trajectories were simpler, the terrain was flatter, the lighting was more predictable. The 6 Apollo landing sites were all within about 26 degrees of the lunar equator, in regions that are, by lunar standards, relatively benign. Flat plains of hardened lava called mare basalts, illuminated by a sun that rises and sets on a 14-day cycle, with temperatures that swing between roughly 260 degrees Fahrenheit in daylight and minus 280 in darkness. Artemis 4 is not going to those places. Artemis 4 is going to the South Pole, and the South Pole of the Moon is a different world. Imagine standing at the rim of a crater near the lunar South Pole. Below you, the crater floor drops away into absolute darkness. Not the darkness of a room with the lights off, but the darkness of a place where sunlight has not reached for billions of years. The sun at the South Pole hangs perpetually near the horizon, casting shadows that stretch for miles, and in certain craters with rims high enough to permanently block the sun's low angle, The interior has been in continuous shadow since before life existed on Earth. Temperatures in these permanently shadowed regions drop to minus 390 degrees Fahrenheit. That's colder than the surface of Pluto. This is where NASA wants to land humans, not because it's easy, it's the most hostile terrain on the Moon, but because of what's hiding in that darkness. The landing itself will be an engineering achievement on a scale that Apollo never attempted. The South Pole terrain is not flat. It's rugged, cratered, strewn with boulders, and sloped at angles that would tip a lander if the touchdown point is wrong by even a few meters. NASA has identified 9 candidate landing regions, each selected based on orbital imagery, terrain mapping, and illumination profiles, because at the South Pole, the difference between a site that gets sunlight and a site that doesn't can be measured in hundreds of feet. The crew will arrive in lunar orbit aboard Orion, dock with the landing vehicle, tested on Artemis 3, and ascend to the surface for a stay of approximately 1 week. That's 2 to 3 times longer than any Apollo surface mission. During that time, they won't just be collecting rocks, though they will do that too. The first sampling of South Pole geology will answer questions that have been open since we first detected anomalies in the data from orbit. Questions about the composition of the regolith, the mineral content of the ancient highland terrain, and whether the geological record at the South Pole preserves information about the early solar system that has been erased everywhere else. But the samples are secondary. The primary objective of Artemis 4 is reconnaissance, not scientific reconnaissance, though it includes that, resource reconnaissance. The crew will deploy a lunar environment monitoring station, an instrument package designed to measure the thermal, radiation, and dust environment at the South Pole over extended periods. They'll map the terrain with ground truth precision that orbital sensors can't match. They'll characterize the regolith, the loose rocky soil that covers the Moon, not just for what it contains, but for how it behaves, how it compacts, how it responds to mechanical processing, whether it can be used as a building material. This is not exploration in the Apollo sense. This is not, let's see what's there. This is, let's confirm that what's there is usable. Because what NASA believes is there, what orbital data strongly suggests is there, is the single resource that makes everything else possible. The resource that transforms the Moon from a place you visit into a place you live. The difference between Apollo and Artemis 4 isn't just the location, it's the intent. Apollo proved we could land on the Moon. Artemis 4 is designed to prove we landed in the only place that matters, the only place where the resources exist to support a permanent human presence, the only place where the economics of space travel change from impossible to merely difficult. And those resources are locked in ice, frozen in craters that haven't seen sunlight in 3 billion years, waiting in darkness so absolute that the molecules themselves barely move. Part 6. The Ice That Rewrites the Moon. 3.5 billion years ago, give or take a few 100 million comets were hitting the Moon. Not occasionally, regularly. The inner solar system was a shooting gallery of icy debris left over from the formation of the planets, and the Moon, having no atmosphere to burn up incoming objects, took every impact at full force. There was no air to slow them down, no weather to erode the craters they left behind. Just rock meeting ice at tens of thousands of miles per hour, over and over, for hundreds of millions of years. Most of what those comets delivered was vaporized on impact. The kinetic energy of a cometary strike converts ice to gas in milliseconds. A chunk of ice the size of a house hits the surface at 40,000 miles per hour, and in the instant of contact it ceases to exist as a solid. It becomes a superheated cloud of vapor, expanding outward in every direction across a world with no atmosphere to contain it. Most of that vapor escapes into space, gone forever. But some of it, a fraction, doesn't escape. Some of that water vapor drifted. Molecules bounced across the surface in lazy ballistic arcs, propelled by the faint energy of sunlight, hopping from one patch of regolith to the next like stones skipping across a pond in slow motion. And some of those molecules, through nothing more than random chance and orbital geometry, found their way into craters near the poles, craters where the sun never shines, where temperatures are so low that a water molecule, once it lands, never leaves. It doesn't evaporate, it doesn't sublimate, it just sits there, frozen into the regolith, accumulating grain by grain over geological time, one molecule at a time, for 3 billion years. Those permanently shadowed craters are cold traps, and the evidence gathered over decades by missions like the Lunar Reconnaissance Orbiter, the Lunar Prospector Neutron Spectrometer, India's Chandrayaan missions, and most recently NASA's Viper rover data strongly suggest that these cold traps contain water ice, not liquid water, not flowing water, ice mixed into the soil, possibly as thin frost layers on individual grains, each one coated in a shell of frozen water, thinner than a human hair, possibly as larger deposits buried under centimetres or metres of dry regolith. The ice doesn't look like ice, it doesn't glitter or gleam, it looks like dirt. Grey, unremarkable lunar dirt that happens to contain, molecule by molecule, the most valuable substance in the solar system. The estimates vary, and they vary a lot. Some models suggest hundreds of millions of metric tons of water ice at the lunar South Pole. To put that in perspective, 100 million metric tons is roughly the volume of a small lake. Others are more conservative, suggesting the ice is diffuse, spread thinly across vast areas, mixed with regolith at concentrations of a few percent by weight. The distribution is almost certainly uneven. Some craters may be relatively rich with ice. Others may contain trace amounts contaminated with ammonia, methanol, or other volatile compounds that arrived alongside the water during those ancient cometary impacts. Nobody knows exactly what's there until someone goes and digs, and that uncertainty, that gap between probably and definitely, is one of the biggest gambles in the history of space exploration. But here's why this changes everything, and I mean everything, not just about the moon, but about how humans operate in space for the rest of our history as a species. And this is where the story connects back to why those astronauts splashing down in the Pacific 4 days ago were not completing a mission but starting one. Water in space is not just something you drink. Water is the most versatile resource in the solar system. Split a water molecule with electricity, a process called electrolysis, which is straightforward and well understood, something a high school chemistry student could explain to you, and you get 2 hydrogen atoms and 1 oxygen atom. Oxygen is what you breathe. Hydrogen and oxygen together, in the right proportions and the right conditions, are rocket fuel. Literally the same propellant mixture that powered the space shuttle's main engines, the same chemistry that lifts rockets off Earth every week. The fuel that could carry a spacecraft from lunar orbit to Mars is potentially sitting in the frozen dirt of a crater that hasn't seen sunlight since before multicellular life existed on Earth. Now think about what that means for the question of coming back. Right now, every kilogram of anything you want on the moon has to be launched from Earth's surface. Earth has a gravity well that requires enormous energy to escape. That's why rockets are so large and so expensive. It costs roughly $10,000 to put a single kilogram into low Earth orbit, and significantly more to send it to the moon. A kilogram of water on the lunar surface launched from Earth might cost $50,000 or more by the time you account for the entire logistics chain, the rocket, the fuel to launch the rocket, the capsule, the landing system, the storage, the ground operations. But a kilogram of water extracted from lunar ice? The cost drops to whatever it takes to mine it, process it, and store it, all using energy from solar panels or a nuclear reactor already on site. The economics aren't even comparable. It's the difference between flying bottled water to a desert island by helicopter every week and digging a well on the island itself. One approach has a cost that scales until it breaks. The other has a cost that shrinks as the infrastructure matures. This is the concept NASA calls in situ resource utilization, ISRU. Using what's already there instead of bringing everything from home. And ISRU doesn't just make lunar habitation cheaper, it makes it possible. Without local resources, a permanent lunar base is a supply chain problem that eventually becomes unsolvable. The cost of maintaining a human presence that depends entirely on Earth-launched consumables grows with every additional crew member, every additional month, every additional system that needs replacement parts or propellant. Eventually the math defeats you. You can't ship enough stuff fast enough to keep a growing outpost alive. With ISRU, with water ice that can be converted to drinking water, breathable oxygen and rocket fuel, the equation inverts. The moon stops being a cost centre and becomes a supply node. A gas station parked 250,000 miles from Earth at the top of a gravity well that's 1/6 as strong. A place where spacecraft travelling to Mars or to the asteroids or deeper into the solar system can stop, refuel and continue without ever returning to the bottom of Earth's gravity well. The moon becomes the last stop on the way out and the first stop on the way in. Not a destination, a hub, and it goes beyond water. Lunar regolith, the soil itself, contains silicon, aluminum, iron, titanium and oxygen bound up in mineral form. Experiments have already demonstrated that regolith can be sintered or 3D printed into structural components using concentrated sunlight or microwave energy. You take the dirt, you heat it until it fuses, and you shape it into bricks, panels, radiation shielding, landing pads. The building material for future lunar structures is, quite literally, the ground you're standing on. You don't ship concrete to the moon, you make it there from the moon. But this is also where the uncertainty lives, and it would be dishonest not to acknowledge it. The entire Artemis architecture, the base, the fuel depot, the deep space refueling concept, the whole vision of the moon as humanity's first permanent outpost, depends on water ice being present in sufficient quantities, in accessible locations, in a form that can actually be extracted and processed with the technology we can deliver to the surface. If the ice turns out to be too sparse, too contaminated with compounds that gum up the processing equipment, too deeply buried under meters of dry rock, or too mixed with regolith to extract economically, then the foundation of the whole plan shifts. Not collapses necessarily, but shifts in ways that could push timelines out by decades. That's a risk NASA is aware of, and it's one of the reasons Artemis 4's resource reconnaissance is so critical. The orbital data is suggestive. The neutron spectrometry shows hydrogen signatures consistent with water. The physics makes sense. Cold traps should trap volatiles, and comets should have delivered them. But suggestive and confirmed are separated by a gap that only boots on the ground can close. Only a human being standing at the rim of a permanently shadowed crater, drilling into the regolith, pulling up a core sample and analysing what's inside will tell us whether the plan works or needs to be rewritten. And there's a philosophical dimension here that's easy to miss in the engineering details. When we talk about water ice on the moon, we're not talking about a scientific curiosity. We're not talking about a fun fact for a textbook. We're talking about the most strategically important substance in the solar system, located in one of the most inaccessible places humans have ever tried to reach. The most valuable real estate out there isn't measured in acres or square miles. It's measured in kilograms of frozen water hiding in permanent darkness at the bottom of craters so cold that the laws of thermodynamics themselves become a storage system. Whoever controls access to that ice controls the future of human expansion beyond Earth. And that's not a theoretical statement. It's not a think tank projection. It's the operating assumption behind every dollar NASA is spending, every rocket being stacked in Florida, every legal framework being negotiated between nations. The ice is why the South Pole matters. The South Pole is why permanence matters. And permanence is why the next humans who go to the moon may never truly come back, not because they're trapped, but because what they find in that darkness is too important to leave behind. Which brings us to the mission where NASA stops pretending this is about exploration. Part 7. The Mission. Where NASA stops pretending. Artemis 5 is scheduled to launch months after Artemis 4, and if you've been paying attention to the pattern, each mission more complex, each stay longer, each objective more permanent, then what Artemis 5 represents shouldn't surprise you. But it should unsettle you, at least a little. Because Artemis 5 is the mission where astronauts stop being explorers and become construction workers. And that distinction explorer versus builder, is not a semantic game. It's the line between visiting a place and committing to it. Once you cross it, the entire logic of the program changes. Explorers come home with stories. Builders come home with a to-do list for the next crew, and that to-do list never ends. The timeline is aggressive. By the time Artemis V's crew arrives at the South Pole, the landing site will already be different from what Artemis 4 found. Not slightly different. Fundamentally different. In the months between missions, a series of robotic cargo deliveries, carried out under NASA's Commercial Lunar Payload Services Program, or CLPS, will have deposited hardware on the surface. Not small instruments, not science packages you can hold in one hand. We're talking about rovers, power generation units, communication relay stations, structural components, panels, connectors, mounting hardware, for what NASA carefully refers to in its documentation as surface infrastructure. But what anyone with eyes and a basic understanding of construction can see is the skeleton of a base. These cargo deliveries are the part of the Artemis program that gets almost no media coverage, and they might be the most important part. While everyone is watching the crewed launches, the astronauts waving, the countdown, the dramatic footage of rocket engines, robotic landers are quietly ferrying the building materials of a permanent human settlement to the lunar South Pole. No fanfare, no live streams with millions of viewers, just payload after payload, landing in the grey dust, deploying their cargo and going silent. By the time a human crew sets foot near those deliveries, there will be equipment scattered across the landing zone that has been sitting in vacuum and temperature extremes for months, waiting to be switched on. And that's exactly what the crew of Artemis 5 will do. They won't be running experiments in the traditional sense. They won't be scooping up soil samples and sealing them in bags for the trip home. They'll be activating systems, walking from one piece of pre-positioned hardware to the next, connecting power cables between solar arrays and habitat modules, checking connector seals, verifying that robotic arms placed equipment correctly during the months when no humans were present. Think about that for a moment. Robots will have been assembling parts of a lunar base autonomously, and the first human task upon arrival is quality control. Inspect what the machines did, fix what they got wrong, finish what they couldn't. They'll be testing the Lunar Terrain Vehicle, a rover designed not for joyrides or photo opportunities, but for work. This isn't the Apollo lunar rover, which was essentially a golf cart with a camera mount. The LTV is a utility vehicle, capable of carrying equipment, tools and astronauts across kilometres of South Pole terrain that is some of the most rugged and unforgiving ground on the Moon. Slopes, boulders, craters with rims that cast permanent shadows. The LTV needs to navigate all of it reliably, because the base components won't all be in one convenient spot. The geography of the South Pole doesn't allow for that. Usable flat ground, solar access, and proximity to shadowed craters are competing constraints, and the base layout will be spread across whatever terrain satisfies the most criteria simultaneously. There's a language shift happening in the NASA documentation that tells you more than any press conference ever will. In the Apollo era, astronauts were called explorers. The word appeared in mission patches, in presidential speeches, in the naming of the lunar module itself, Explorer. In the shuttle era, the terminology shifted to mission specialists and payload commanders, technical language for a technical program. But in the Artemis documentation, particularly for Phase 2 and Phase 3, the language drifts again toward operators, technicians, crew, not explorers of the unknown, operators of known systems, technicians maintaining equipment, crew rotating through shifts. The vocabulary of exploration is being quietly replaced by the vocabulary of industry. And nobody at NASA is holding a press conference to announce this shift, because the announcement would raise questions that the program isn't ready to answer publicly. Questions about long-term cost, not the cost of a single mission, but the cost of maintaining a permanent human presence on the Moon for decades. Questions about commitment. What happens when a new administration takes office and wants to redirect funding? Questions about ethics. what it means to build a settlement on another world while millions of people on this one lack clean water, stable housing, or reliable electricity. These are uncomfortable questions, and the easiest way to avoid them is to keep using the word exploration for as long as possible, even when the work being done has nothing to do with exploring and everything to do with building. But the shift is happening regardless of whether it's announced. You can see it in the crew selection criteria that are beginning to emerge. Artemis V's crew manifest, when it's finalised, will likely include astronauts selected not just for their piloting skills or their scientific credentials, though those still matter, but for their ability to perform physical construction tasks in a spacesuit, in 1/6 gravity, in an environment where the temperature outside the suit can swing by 500 degrees depending on whether you're standing in sunlight or shadow. In an environment where a torn glove doesn't mean a bad day, it means death by decompression in under a minute. The physical demands of construction work on the Moon are something NASA has studied extensively in simulation, but has never tested in the real environment for extended periods. Apollo astronauts found that working in lunar gravity was exhausting in ways they hadn't anticipated. The suits were stiff, the gloves made gripping tools difficult, and the fine lunar dust worked its way into every joint and seal, degrading equipment faster than expected. Artemis V's construction tasks will be longer, more complex and more physically demanding than anything Apollo attempted, and they'll be performed by people who've been living in microgravity during the transit from Earth, whose muscles and cardiovascular systems have already begun the deconditioning process that starts within hours of leaving normal gravity. The work they'll do represents a psychological milestone that's easy to overlook if you're focused on the engineering. When astronauts are exploring, collecting samples, taking photographs, running experiments, describing what they see, there's an implicit understanding that they're visitors, guests. They came, they observed, they'll leave, and the place they visited will be exactly the same after they're gone as it was before they arrived. That's what exploration means. You don't change the place changes you. But when astronauts are building, connecting systems, activating infrastructure, bolting panels together, testing power lines, preparing a site for the next crew, the implication inverts completely. You don't build something you intend to abandon. Nobody pours a foundation and walks away. Construction is a commitment to the future. It says, louder than any speech or mission statement, someone is coming after us, and they'll need this to work. Every cable connected, every system activated, every piece of hardware verified is a promise to a future crew that this place will be here, functional and waiting when they arrive. And that promise is what makes Artemis 5 the true point of no return, not in the physical sense, but in the programmatic sense. After Artemis 5, the South Pole site will not be a landing zone. It will be a work site. There will be equipment on the surface that runs continuously, drawing power, collecting data, maintaining thermal equilibrium, equipment that can't just be switched off and forgotten. There will be systems that need monitoring, first by remote operators sitting at consoles in Houston or Huntsville, and eventually by rotating crews on the surface itself. There will be power systems that need to stay online through the 2-week lunar night, 14 Earth days of continuous darkness, where temperatures plummet to hundreds of degrees below zero, and solar panels produce exactly nothing. That challenge, keeping a base alive through the lunar night, is so severe that it requires its own dedicated solution. A solution that brings with it a technology humanity has been both using and fearing for 80 years. A technology that, once deployed on the lunar surface, creates a dependency so fundamental that it reshapes the entire relationship between the crew and the place they're living. This is the moment astronauts stop visiting the Moon and start working there. And once work begins, once the first cable is connected, the first system goes live, the first habitat draws power from a source that can't be paused, a new kind of dependency emerges. Not a dependency on Earth, not a dependency on the next resupply mission, a dependency on the infrastructure beneath your feet. Infrastructure that only functions if someone is there to maintain it. Infrastructure that, if abandoned, doesn't just go dormant, it fails. And when it fails, everything that depends on it fails too. The machines that make this possible, and the single point of failure they represent, are worth understanding in detail. Because once you see what keeps a lunar base alive when the sun disappears for 2 weeks, you'll understand why leaving stops being a simple decision and starts being a calculated risk. Part 8. The machines that keep you alive when the sun disappears. The moon has a day-night cycle, but it's nothing like Earth's. On Earth, you get roughly 12 hours of light and 12 hours of darkness, give or take depending on the season and your latitude. You barely think about it. The sun goes down, you turn on a lamp, you go to sleep, and by the time you've had your coffee the next morning, the sun is back. The infrastructure of human civilization, the power grid, the food supply, the heating systems, is built around a cycle that resets every 24 hours. We take that rhythm so completely for granted that most of us have never considered what happens when it disappears. On the moon, a single lunar day, sunrise to sunrise, lasts approximately 29.5 Earth days. That means roughly 14 days of continuous sunlight followed by 14 days of continuous darkness. Not the kind of darkness you experience at night on Earth, where the atmosphere scatters light from cities and stars and the moon itself provides a soft glow. Lunar darkness is total. There is no atmosphere to scatter anything. When the sun drops below the horizon at the South Pole, below the jagged rims of craters that haven't been reshaped by wind or water in 4 billion years, it doesn't fade gradually like a sunset. It vanishes, and what replaces it is an absolute unbroken blackness that lasts for 336 hours. During the lit half of the cycle, solar panels work, equipment runs, temperatures at the South Pole in illuminated areas hover at levels that spacesuits and habitats can manage, still extreme by Earth standards, but within the engineering tolerances of the systems NASA is designing. Then the sun drops below the crater rims, and everything changes. Temperatures plummet. In the permanently shadowed regions, they fall to minus 390 degrees Fahrenheit, but even in areas that receive sunlight during the day, the nighttime temperatures drop to minus 280 or lower. Any system that depends on solar energy shuts down. Anything that can't survive the cold, and most electronics, most mechanical systems, most of the equipment humans rely on, breaks. Seals contract, lubricants freeze, batteries drain. The entire operational capacity of a solar-powered base drops to zero and stays there for 2 weeks. Batteries help, but current battery technology can't store enough energy to power a base for 14 days, not even close. The energy density of the best lithium-ion batteries available, the same chemistry that powers your phone, your laptop, electric cars, would require a battery bank so massive that the cost of launching it from Earth would dwarf the entire Artemis budget. You'd be shipping thousands of kilograms of batteries to the moon just to keep the lights on for 2 weeks, and then you'd need to do it again when those batteries degrade, which they would, because batteries in extreme thermal environments degrade faster than batteries on Earth. Which is why NASA is bringing a nuclear reactor. And this is where the story of permanence, the reason the next humans on the moon may never truly come back, acquires its most literal and unavoidable dimension. The Fission Surface Power Project, developed in partnership with the Department of Energy and contracted through private industry, is designed to provide approximately 40 kilowatts of continuous electrical power on the lunar surface. 40 kilowatts is not a lot by earthly standards. It's roughly what 3 or 4 American homes consume on an average day. Your air conditioning system alone might draw 5 or 6 kilowatts on a hot afternoon. But on the moon, where every watt has to be produced locally, where there is no grid to tap into, no backup generator you can rent from a hardware store, 40 kilowatts is the difference between a base that survives the lunar night and one that freezes in the dark with its crew inside. The reactor itself is roughly the size of a car, not a truck, not a building, a car. It uses a uranium core, enriched to levels well above what commercial reactors use on Earth. We're talking about weapons-grade enrichment levels, which is one of the reasons the project involves the Department of Energy and not just NASA. The reactor converts thermal energy from nuclear fission to electricity through a process that doesn't require water cooling. This is critical, and it connects directly back to the ice we just talked about, because water on the Moon is far too valuable to circulate through a cooling system and lose to evaporation or leakage. Every drop of water on the lunar surface is drinking water, breathing oxygen or rocket fuel. Wasting it as industrial coolant would be like burning $100 bills to heat your house when you're sitting on a pile of firewood. Instead, the system uses heat pipes, sealed tubes containing a working fluid that absorbs heat at one end, evaporates, travels to the other end, condenses and returns, and large radiator panels that reject waste heat into the vacuum of space. In vacuum, there's no air to conduct heat away, so the radiators work purely through thermal radiation. They glow in the infrared, shedding energy into the void. It's thermodynamically efficient but mechanically complex because heat pipes and radiators have moving parts, seals, joints, and surfaces exposed to the full spectrum of lunar hazards. Micrometeorite impacts, thermal cycling, and the ever-present abrasive dust that works its way into everything. The plan is to bury the reactor under several feet of regolith once it's deployed. The lunar soil serves double duty as radiation shielding, protecting the crew from the neutron and gamma radiation that the reactor emits during operation, and as thermal insulation, helping to buffer the extreme temperature swings between day and night. In theory, a properly buried and configured reactor can operate continuously for years without hands-on maintenance, providing uninterrupted power to habitat modules, life support systems, ISRU processing equipment, communication relays, and lighting, regardless of whether the sun is shining. Day or night, summer or winter, not that the Moon has seasons, but you understand the point, the reactor runs. In theory. The failure scenarios are worth sitting with, because they illustrate a dependency that fundamentally changes the nature of what it means to be on the Moon. And this is the part of the permanent story that doesn't show up in the promotional videos. If the reactor's heat rejection system fails, if a radiator panel is damaged by a micrometeorite strike, which is not unlikely over a multi-year operational period, given that the Moon has no atmosphere to burn up incoming debris, the reactor begins to overheat. If a heat pipe develops a leak, the thermal balance shifts. If the management software malfunctions, the automatic controls that regulate the fission reaction could respond incorrectly. In any of these scenarios, the reactor's safety systems trigger an automatic shutdown. The reactor stops producing power. And if that shutdown happens during the lunar night, during those 14 days of darkness, when solar panels produce nothing, the base goes dark. No power means no life support. No CO2 scrubbing, no oxygen generation, no temperature regulation. The interior of the habitat begins to cool immediately, and in the vacuum-insulated environment of the Moon, cool means a descent toward temperatures that will freeze human tissue in hours. The crew has a window, maybe hours, probably not days, to restore the reactor, switch to emergency backup power if it exists and is sufficient, or evacuate. But evacuate to where? This is the question that reveals the trap. The lander that brought them needs power to maintain its propellant conditioning. Rocket fuel at cryogenic temperatures doesn't stay cold by itself. The rover needs power to move. The communication systems that connect the crew to mission control on Earth, the only lifeline for troubleshooting, for guidance, for emotional support in what would be the most terrifying night in human history, need power to transmit. Every single system at the base ties back to the reactor. Pull that one thread, and the whole fabric unravels. NASA will build in redundancies. There will be backup power units, emergency battery banks, manual overrides, contingency procedures rehearsed hundreds of times on Earth. But the fundamental architecture is clear, and no amount of redundancy changes it. Survival on the Moon is tethered to fixed infrastructure, not to the spacecraft that brought you, not to Earth, which is 240,000 miles and 3 days away by the fastest available vehicle, to the machinery on the ground around you, the reactor beneath the regolith, the habitat connected to the reactor, the life support connected to the habitat, your lungs connected to the life support. It's a chain, and every link is bolted to the moon. And this is the connection to the larger story that matters most. Once your survival depends on infrastructure that's bolted to the lunar surface, infrastructure you built, that you maintain, that you can't fold up and take with you, the psychology of your presence undergoes a fundamental shift. You're no longer a visitor who could leave at any time, the way Apollo astronauts were. Apollo's crew carried their survival on their backs. The lunar module was self-contained, independent of anything on the surface. They could leave whenever they wanted. They depended on nothing that stayed behind. Artemis crews won't have that freedom. They'll be residents whose lives depend on systems that only work if someone stays and maintains them. Leaving doesn't just mean going home. It means abandoning the reactor that powers the habitat. Abandoning the habitat that shelters the next crew. Abandoning the ISRU equipment that's slowly processing ice into fuel for future missions. Every departure is a risk to everyone who comes after you, unless someone replaces you before you leave. The reactor creates permanence not through any grand declaration, not through intent or ideology, but through the simplest and most unbreakable force in human decision-making: dependency. Once it's running, someone always has to be there, or at least available to return quickly, because the systems it powers don't pause. They don't hibernate. They don't wait politely for the next crew to arrive. They run, or people die. And if the systems are keeping ice processing equipment operational, producing fuel and oxygen that future missions depend on, then shutting them down doesn't just risk the current crew. It breaks the supply chain for every mission that follows. Now imagine standing on the surface during the lunar night. Picture it as concretely as you can. No sunlight, no Earth in the sky. Depending on your location and the time of month, sometimes the Earth hangs above the horizon, a blue-white marble roughly 4 times the size of the moon, as seen from Earth, but sometimes it's below the horizon, and you can't see it at all. The only illumination comes from work lights mounted on the habitat exterior, and the rover, powered by the reactor humming under the regolith beneath your feet. You can feel nothing through the suit, no wind, no temperature, no texture, but you know that the ground you're standing on is 250 degrees below zero, and the only thing between you and that cold is a few layers of insulated fabric and a heating system that draws power from the same reactor that keeps the habitat alive. The stars above you are brighter and more numerous than any human on Earth has ever seen, because there's no atmosphere to scatter their light, no light pollution to wash them out. The Milky Way isn't a faint smudge, it's a river of light so dense it looks solid. The horizon is close, the moon is small, only about a quarter of Earth's diameter, and the curvature is noticeable even at eye level. Beyond the circle of artificial light cast by your work lamps, there is nothing. Not darkness in the way you experience it on Earth, where your eyes adjust and shapes slowly emerge. Absolute, unbroken, featureless nothing in every direction, stretching to a horizon that's closer than you'd like. That image, a small pool of human-made light on the surface of another world, powered by controlled nuclear fission, surrounded by a void that would kill you in 90 seconds without your suit, is the image of the future NASA is building toward. Not flags and footprints, not a 3-day visit with a commemorative plaque. A settlement, fragile and dependent, clinging to existence through engineering and will and the quiet hum of a reactor that must never stop. And as with any settlement in any era of human history, the question of who owns it, who controls the land, who makes the rules, who gets to decide what happens there and who is excluded, is already being answered. Quietly, carefully, in conference rooms and legal offices very far from the lunar surface. Part 9, Claiming Land Without Calling It a Claim. In 1967, at the height of the Cold War and the space race, when the United States and the Soviet Union were lobbing rockets into orbit, with the kind of competitive fury that only existential rivals can sustain, the United Nations did something quietly remarkable. They got both sides and over 100 other nations to sign a piece of paper that said, essentially, nobody owns space. The Outer Space Treaty, as it came to be known, is a document that most people have never read, most lawmakers have never studied, and most space enthusiasts have never examined beyond the broad strokes. But it governs, in theory, everything humanity does beyond Earth's atmosphere. Every satellite, every space station, every probe, lander, rover, and astronaut that has ever left this planet has operated under its framework. The core principle is simple and was, at the time, genuinely revolutionary. No nation can claim sovereignty over any celestial body. The moon doesn't belong to America, even though Americans planted flags on it. It doesn't belong to Russia, even though Soviet probes reached it first. It doesn't belong to China or Europe or India or anyone. It is, in the treaty's own language, the province of all mankind. A shared inheritance. Common ground in the most literal sense of the phrase. That principle has held for nearly 60 years. Through the end of the Apollo program, through the shuttle era, through the construction of the International Space Station, through decades of robotic exploration, no nation has formally claimed territory on the moon or any other celestial body. The treaty worked. But here's the thing about legal frameworks that were built to govern a world that no longer exists. They hold exactly as long as nobody has a reason to test them. And the reason to test this one is now sitting in craters at the lunar South Pole, frozen in darkness, worth more than any territory on Earth. The Outer Space Treaty was written for an era when going to the moon was a stunt. A magnificent, awe-inducing, historically significant stunt, but a stunt nonetheless. A geopolitical flex that lasted a few days, left behind nothing but flags and footprints and tyre tracks, and then ended. Nobody stayed. Nobody built anything permanent. Nobody extracted resources. The treaty didn't need to address property rights or territorial control, because no one was doing anything on the moon that required property rights or territorial control. You can't own what you can't hold, and no one was holding anything. The treaty was never designed for a world where someone might actually stay. And the cracks in that framework, hairline fractures that have been forming for over a decade, are now wide enough to walk through. In 2015, the United States Congress passed the Commercial Space Launch Competitiveness Act. It's a law that, among many provisions, does something that would have been unthinkable in 1967. It explicitly grants US citizens the right to own resources extracted from celestial bodies. Not the land, not the crater, not the territory, not the mineral rights in the way a mining company owns mineral rights on Earth. Just the stuff you dig up, the actual physical material that you extract from the regolith, process through your equipment, and store in your tanks. You don't own the mine, but you own the ore. It's a careful distinction. Careful in the way that a lawyer is careful when they're threading a needle between what a treaty says and what a nation wants to do. The law doesn't claim sovereignty over the moon. It doesn't violate the letter of the Outer Space Treaty. But it creates, for the first time in history, a legal framework for property rights on a celestial body without calling them property rights. And it was passed with relatively little fanfare, no major news coverage, no public debate, no protests. Most Americans don't know this law exists, but its implications are enormous, because once you establish the legal principle that resources extracted from the moon belong to the entity that extracts them, you've created an incentive structure that leads, inevitably, to the question the treaty was designed to prevent. Who controls the territory where those resources are found? And this connects directly to why the next humans on the moon may never come back. Because coming back implies the moon is a place you visit, a place nobody owns, nobody controls, a place that belongs to everyone equally. The legal architecture being built right now is quietly demolishing that assumption. Then came the Artemis Accords. Introduced by NASA in 2020 and signed initially by 8 nations, the Accords are a set of bilateral agreements between the United States and partner nations, over 40 signatories as of 2026, including the United Kingdom, Japan, Australia, Canada, Italy, South Korea and Brazil, among others, that establish guidelines for how nations should conduct themselves on and around the Moon. They cover transparency in operations, interoperability of systems so different nations' equipment can work together, registration of space objects, sharing of scientific data, the mitigation of orbital debris, and one concept that deserves particular careful attention: safety zones. A safety zone, in the Accords framework, is a temporary area around a lunar operation, a landing site, a mining operation, a base, where other nations agree to coordinate before entering. The idea, on its surface, is perfectly reasonable. You don't want another country's rover driving through your landing site while your astronauts are outside doing EVAs. You don't want a competing mining operation kicking up debris that damages your solar panels. You don't want two nations' activities interfering with each other in an environment where interference can be lethal. Safety zones are, in the most charitable reading, a common-sense measure to prevent accidents. But the practical effect is something else entirely, and this is where you have to look past the language and into the geometry of the situation. A safety zone around a temporary landing site, a small perimeter that exists for a few days while a crew is on the surface and then dissolves when they leave, is genuinely temporary. It's a parking spot, reserved while you're using it, available to others when you're gone. That's what the Accords describe. That's the version that 40-plus nations agreed to. But a safety zone around a permanent base, a base with a nuclear reactor buried under the regolith, ISRU equipment processing ice into fuel and oxygen around the clock, habitat modules housing rotating crews for months at a time, rovers operating across kilometers of terrain, communication relays maintaining constant contact with Earth. That safety zone is not temporary. It's not a parking spot. It's a controlled territory. And it doesn't matter what you call it in the legal documents, what diplomatic language you wrap it in, what careful distinctions you draw between sovereignty and coordination. If you've built infrastructure that your astronauts depend on for survival, and you've established a zone around that infrastructure where other nations cannot operate without your knowledge and your permission, you've created a de facto territorial claim. You own the land in every way that matters except the name. The analogy isn't perfect, but think of it this way. Imagine someone sets up a homestead on unclaimed land that belongs in theory to everyone. They build a house, they dig a well, they put up a fence, they bring in equipment, clear the ground, set up a workshop. Then they tell their neighbours, I don't own this land, but for safety reasons, for everyone's protection, please don't come within 500 feet of my house without checking with me first. Just coordinate with me before you approach, and we'll work it out. Technically, they haven't claimed ownership. They've made no legal filing. They've asserted no sovereignty. But practically, they control the territory. They decide who enters. They decide what activities are allowed nearby. They built the only well in the area, and if you want water, you need to deal with them. Now shrink the available land. Imagine that in this entire region, hundreds of square miles of terrain, there are only a handful of spots where you can dig a well. Only a few locations where the water table is accessible, where the ground is stable enough to build on, where the conditions allow for permanent settlement. Whoever builds at one of those spots first doesn't just gain a place to live. They gain leverage, strategic leverage, because every other potential settler who arrives later has fewer options, and every option they have is further from the water. That's the south pole of the Moon. The number of sites that offer both adequate solar illumination, peaks and ridgelines that catch sunlight even when the sun is near the horizon, and access to permanently shadowed craters with confirmed or suspected water ice deposits is limited. Current analysis, based on data from the Lunar Reconnaissance Orbiter and other missions, suggests fewer than a dozen truly viable locations for a permanent base. Some estimates put the number even lower, 6 or 7 sites that meet all the criteria for long-term human habitation with ISRU capability. Whoever establishes infrastructure at one of those sites first doesn't just gain a foothold, they gain control over the most strategically important real estate in the solar system. And control here doesn't mean military control. Nobody's talking about weapons on the Moon, at least not yet. It means practical control, operational control. The kind of control that comes from being there, having your equipment running, having your safety zone established, having your legal framework signed by 40 nations who've agreed to coordinate with you before entering your perimeter. The kind of control that makes it technically possible for anyone else to come. The Outer Space Treaty still guarantees freedom of access, but practically difficult to compete. The Artemis Accords are, in this light, not just safety guidelines. They're not just best practices for responsible lunar activity. They are the legal architecture for a first-mover advantage that could define the geopolitics of space for the next century. The United States isn't just building a base on the moon. It's building the rules. It's writing the norms that will govern how every nation interacts with the lunar surface, and it's doing so while simultaneously being the only nation with a credible near-term plan to put humans at the South Pole. The rules, as written, favour the entity that arrives first, builds first, establishes presence first, and sets the norms that everyone else has to follow. There are ethical dimensions here that the programme's cheerful public messaging, the inspirational videos, the smiling astronauts, the for all mankind rhetoric doesn't address. Is this colonisation? The word carries weight. Centuries of weight, soaked in exploitation and displacement, and the erasure of existing cultures. There are no indigenous peoples on the moon to displace. There are no ecosystems to destroy. There's no one to exploit, no culture to erase, no existing claim to override. In that sense, the comparison to terrestrial colonialism is imperfect and arguably unfair. But the pattern, the structural pattern, stripped of its specific historical context, is familiar enough to make historians and ethicists uncomfortable. Arrive first, establish presence, extract resources, build infrastructure that creates dependency, create legal frameworks that normalize your position, set the terms for everyone who follows, benefit from the advantage of having been there while others weren't. That's a pattern that has repeated itself across continents and centuries, and its outcomes have never been equitable, even when the initial intentions were benign. The question isn't whether lunar settlement is morally equivalent to the colonization of the Americas or Africa. It isn't, for many important reasons. The question is whether the structural dynamics lead to similar concentrations of power and access, and whether anyone is designing safeguards to prevent that. The Antarctic Treaty System offers an instructive parallel and also a cautionary one. Antarctica, like the Moon, is governed by an international agreement that prohibits sovereignty claims and mandates peaceful use for scientific purposes. And for decades, it's worked. No nation has formally claimed Antarctic territory, though several maintain research stations that look suspiciously like permanent settlements, and the question of mineral rights under the ice has been deliberately deferred rather than resolved. The system holds because the incentive to defect is low. Antarctica has scientific value, strategic value, and symbolic value, but it doesn't have resources that are worth the diplomatic cost of breaking the treaty to extract. The Moon is different. The Moon has water ice that can be converted into rocket fuel, breathable oxygen, and drinking water. The Moon sits at the gravitational crossroads of every future deep space transportation route. It's easier to reach Mars from the Moon than from Earth, in terms of the energy required. The Moon has regolith that can be processed into building materials, metals that can be refined, and a position in cislunar space that gives it strategic military and communication significance. The incentives to control lunar resources are not theoretical, they are operational. They are being acted on right now, in the form of rockets being built, bases being designed, and legal frameworks being signed. The mechanisms to enforce shared access, to ensure that the province of all mankind remains genuinely shared, and not just nominally shared, are, at the moment, non-existent. The Outer Space Treaty has no enforcement body. The Artemis Accords are voluntary. There is no lunar equivalent of the United Nations Security Council, no peacekeeping force, no court with jurisdiction over territorial disputes 240,000 miles from Earth. The rules are whatever the nations involved agree to, and the negotiations are happening between parties with vastly unequal capabilities. When the country that can actually get to the South Pole writes the rules for how the South Pole should be governed, the outcome is not in doubt. The first base at the South Pole won't just survive. It won't just process ice and generate power and house-rotating crews. It will define the rules for everyone who follows, which nations can operate nearby, how close they can build, what resources they can access, what norms they must follow. It will be the precedent, the template, the fact on the ground literally that shapes international space law for generations, and the entity building that base, with the most advanced hardware, the most aggressive timeline, the deepest pockets, and the legal framework already signed by over 40 nations, is the same one that just celebrated a splashdown in the Pacific 4 days ago, while the world applauded a homecoming. But they're not the only ones with a plan, and the other plan is moving faster than most people realize. Part 10. The race you're not supposed to notice. China's lunar program doesn't announce itself the way American missions do. There are no long pre-launch countdown shows filled with commentary, no emotional camera cuts to families watching from mission control, no carefully staged post-flight celebrations. Instead, it unfolds with a kind of disciplined quiet. Missions are announced, executed and concluded with minimal spectacle. And if you're paying attention, that silence starts to feel less like restraint and more like intention. Because while one program tells a story, the other is building one. Over the last decade, China has carried out a sequence of lunar missions that, on the surface, look like straightforward scientific exploration. But when you zoom out and look at them as a series, a pattern begins to emerge, one that mirrors, almost step for step, the same foundational architecture behind NASA's Artemis program. The difference is not in the ambition, but in how openly that ambition is framed. Where NASA talks about sustained presence, China talks about scientific progress. But the hardware being developed, the capabilities being demonstrated, and the timeline being pursued all point in the same direction. In 2019, the Chang'e 4 mission achieved something no nation had done before, a soft landing on the far side of the moon. This wasn't just a symbolic milestone. The far side presents a unique set of technical challenges. There is no direct line of communication with Earth, which means any mission there requires a relay satellite positioned in lunar orbit. China deployed exactly that, Kuehiao, a communications relay satellite, before attempting the landing. That sequence matters. It shows not just the ability to reach difficult terrain, but to build the supporting infrastructure required to operate there consistently. Then, in 2020, Chang'e 5 successfully returned lunar samples to Earth, marking the first time since the Soviet lunar missions of the 1970s that any country had achieved this. Sample return missions are not trivial. They require a fully integrated system, landing, drilling or scooping material, launching back into lunar orbit, docking with an orbiter, and then returning safely to Earth. Each of those steps is a standalone challenge. Together they represent a complete rehearsal of the kind of operations required for crewed missions. And then, in 2024, Chang'e 6 extended that capability even further by returning samples from the far side of the moon, again a first. That mission combined the complexities of both previous achievements, operating on the far side with relay communications and executing a full sample return sequence. It's easy to see these missions as isolated achievements. It's harder, but more accurate, to see them as a layered progression. Each one builds directly on the last, reducing uncertainty, validating systems, and moving incrementally closer to sustained human operations. This is the part that often gets lost in casual coverage. These missions are not stunts. They are capability demonstrations, precision landing, autonomous surface operations, sample acquisition, ascent from the lunar surface, orbital rendezvous, Earth return. These are the exact same building blocks required for putting humans on the moon and bringing them back safely. When you line them up, mission by mission, what you're looking at is not a collection of scientific experiments. You're looking at a checklist. China has been clear, at least in broad terms, about where this is going. The stated goal is to land astronauts on the Moon by around 2030. To support that, they are developing a new generation of hardware, a heavy-lift launch vehicle capable of sending large payloads beyond low Earth orbit, a next-generation crewed spacecraft designed for deep space missions, and a lunar lander built specifically for human descent and ascent. None of this is speculative. These are active programs, with test milestones already underway. And this is where the central thread of this entire story tightens. Because the race to the Moon, specifically to the lunar South Pole, is not just about science or exploration or even national prestige. It's about positioning. The South Pole is not like the equatorial regions explored during the Apollo era. It is geologically complex, permanently shadowed in places, and most importantly believed to contain significant deposits of water ice. But not every location at the South Pole is equally useful. The ideal sites are those rare areas where two conditions overlap: access to ice in nearby shadowed craters, and near continuous sunlight on elevated terrain for power generation. There are not dozens of these locations, there are a handful, and in a legal environment governed by the Outer Space Treaty, which prohibits national sovereignty over celestial bodies, but supplemented by newer frameworks like the Artemis Accords, which introduce the concept of safety zones, physical presence begins to matter in ways the original treaty never fully anticipated. A base, once established, is surrounded by an operational perimeter. Other actors are expected to coordinate before entering that space. It's not ownership, at least not in name, but in practice, it functions as control, which means that being first is not just symbolic, it's structural. NASA's current timeline places a crewed landing at the lunar South Pole through Artemis 4 around 2028. China's stated target for a crewed landing is approximately 2030. On paper, that gives the United States a 2-year lead. At a glance, that margin feels comfortable. But when you factor in the history of delays in large-scale space programs, it becomes much less so. The Artemis program itself has already experienced significant schedule shifts. Artemis 1 was delayed by years due to technical and logistical challenges. Artemis 2, despite its success, slipped from its original launch window. The Space Launch System, the Orion capsule, and the Human Landing System, particularly the complexity of refueling a Starship HLS in orbit, have all faced development hurdles. Each delay compresses that 2-year margin, and in a program where multiple critical systems must align perfectly, delays are not hypothetical, they are expected, so that 2-year lead is not a cushion, it's a razor's edge. Publicly, NASA is careful about how it frames all of this. The language is deliberate. This is not a race. This is about science, about international cooperation, about humanity's return to the Moon. And all of that is true, to a degree. But it's not the whole picture. Because if you look not at the messaging, but at the scale of investment, the tens of billions of dollars, the sustained political backing across multiple administrations, the integration of international partners into a shared architecture, it starts to resemble something else. It starts to resemble a strategic initiative. And strategic initiatives, by definition, have competitors. China's program rarely acknowledges this dynamic publicly. NASA acknowledges it carefully, often in congressional hearings or budget justifications rather than public-facing messaging. But the underlying reality is difficult to ignore. Two independent systems are being built in parallel with overlapping goals, targeting the same region of the Moon within the same narrow window of time. The quiet part, the part that doesn't make it into press releases, is that permanence is the objective because permanence is the advantage. A mission that visits the Moon and returns is a demonstration. A mission that builds infrastructure and stays is a foothold. And a foothold, once established, changes the rules for everyone who comes after. Because once a base exists, once power systems are deployed, communication networks established, resource extraction begins, and safety zones are defined, the conversation shifts. It is no longer about reaching the Moon. It is about operating on it, maintaining presence, expanding capability. And in that context, the idea of coming back starts to lose its relevance, not because astronauts physically can't return to Earth, but because the system they are part of no longer prioritizes return as the endpoint. The strategic imperative becomes continuity, and that leads to the question this entire story has been building toward, quietly, almost in the background, behind the missions and the hardware and the timelines. What does it actually look like when humans stop coming back? Part 11. The first humans who don't come back. Let me be precise before going any further, because the title of this video can be misunderstood in a way that distorts what's actually happening. Nobody is being sent on a one-way mission. There is no version of the Artemis program at any stage where astronauts are launched to the moon without a way to return. Every crewed mission has a return vehicle. Every flight profile includes abort options. Every system is designed, tested, and redundantly engineered around the assumption that the crew comes home. From an engineering standpoint, never come back is simply not true. But this story isn't about engineering. It's about trajectory. It's about the direction a system is moving once it becomes self-sustaining. It's about the difference between a place you visit and a place you inhabit. And it's about how, at a certain point, the question stops being, can we get back, and becomes, why would we leave? That shift doesn't happen all at once. It doesn't happen on a single mission. It emerges gradually, almost quietly, from the structure of the program itself. NASA calls the final phase of Artemis sustained presence, with a target beginning around 2032. The phrase sounds cautious, almost temporary. But what it describes is anything but. Sustained presence means a permanent operational footprint. It means crew rotations instead of isolated missions. It means multiple launches per year, synchronized logistics, and a base that remains active regardless of which specific individuals are there at any given time. In practical terms, it looks like this. A crew arrives at the lunar South Pole and doesn't build a base from scratch. The base is already there. Power systems are running. Habitation modules are pressurized. Communication links are stable. Equipment has been pre-positioned by robotic cargo missions. The crew steps into an environment that is already functioning, already alive with systems that have been operating before they arrived and will continue operating after they leave. They stay not for a week, not for a brief scientific excursion, but for months. They work. They maintain systems. They expand infrastructure. And when their time is up, they don't shut anything down. They hand off to the next crew. The next crew arrives before the previous one leaves, or shortly after, and picks up exactly where they left off. The systems never power down. The lights never go out. The moon, at least in that one small region, never goes quiet again. This is not exploration in the Apollo sense. It's continuity. The closest analogy we have is the International Space Station, where human presence has been continuous for decades. No single astronaut stays forever, but the station itself is never empty. There is always someone on board, always work being done, always systems being monitored and maintained. The presence is not tied to individuals, it's tied to the infrastructure. Artemis extends that model 250,000 miles away from Earth. And when you extend that model, something subtle but profound happens. You create a category of person that didn't exist before. Not an astronaut on a mission, an astronaut on a rotation. The distinction sounds small, but it changes everything. A mission has a defined beginning and a defined end. It's a discrete event. You train for it, you execute it, and you come home. A rotation, by contrast, is part of an ongoing system. You are not the event. You're a temporary participant in something that continues whether you are there or not. Missions end. Rotations don't. Once that shift occurs, the meaning of going to the moon begins to change. It stops being a singular achievement and becomes a routine transfer, like boarding a flight to a remote research station, like shipping out to an offshore platform. The extraordinary becomes operational, and over time, the people who go begin to change as well. At the beginning, the crews will look familiar. Career astronauts, selected through rigorous national programs trained for years, rotating through on government-funded missions. Highly visible, highly curated, still carrying the symbolic weight of exploration. But as the infrastructure grows, power systems stabilizing, habitats expanding, resource extraction becoming more reliable, the skill sets required on the Moon start to diversify. You need engineers who specialize not just in spacecraft systems, but in maintaining specific pieces of lunar infrastructure. Power engineers who understand the behavior of a small nuclear reactor operating in vacuum. Mechanical specialists who can repair and adapt equipment exposed to extreme thermal cycling. Geologists who aren't just collecting samples, but mapping and characterizing ice deposits over extended periods. Technicians who operate extraction systems that turn regolith and ice into usable materials, oxygen, water, fuel. You need medical personnel who are not just trained for emergencies, but for long-term monitoring. People who can track how the human body responds to months in 1/6 gravity, to chronic exposure to elevated radiation, to an environment where every variable is artificial and every failure has consequences. These are not short-term roles. They don't fit neatly into a 1-week or even 1-month mission. They require continuity, expertise that builds over time, familiarity with systems that evolve gradually, not in discrete jumps. And as those roles become more specialized, the identity of the people performing them shifts. They are still astronauts, technically. But the word starts to feel less precise. They are operators, residents, workers in an environment that is no longer purely experimental, but increasingly operational. At some point, and this is where we move from confirmed plans into informed projection, the balance tips. The Moon stops being a place where humans conduct missions and becomes a place where humans maintain a presence. Not permanently in the sense that no one ever leaves, but permanently in the sense that someone is always there. And once that happens, something else begins to change. Not in the hardware, not in the mission profiles, but in the way the people involved think about where they are. Home is not just a physical location, it's a center of gravity for your daily life. It's where your routines are anchored, where your relationships are formed, where your work has context. For the first generation of lunar crews, that center will still be Earth. The Moon will be an assignment, a destination, a place they go for a defined period before returning to their baseline life. But for the generations that follow, those who spend longer rotations, who return multiple times, who build careers around operating and expanding lunar infrastructure, the center begins to drift. Earth becomes the place you visit between rotations. The Moon becomes the place where your work happens, where your expertise matters, where your daily life unfolds. That inversion is subtle at first. It doesn't show up in official documents. It doesn't appear in mission briefings. But it appears in behavior, in language, in the way people describe where they've been and where they're going. And when that inversion happens for even one person, the title of this video stops being metaphorical. Because never come back no longer means being physically unable to return. It means that returning is no longer the point. You go back to Earth, yes, but it's not the end of the story. It's an interlude. The real story continues somewhere else. The health implications of this shift are serious, and in many ways not fully understood. Short-duration missions like the 10 days of Artemis 2 provide data points. They tell us how the human body responds to brief exposure to deep space radiation, to microgravity, to confinement. But they don't tell us what happens over months or years or repeated cycles of exposure. Radiation is the most immediate concern. Outside the protective envelope of Earth's magnetosphere, astronauts are exposed to higher levels of cosmic radiation. On Artemis 2, preliminary measurements suggested around 12 millisieverts over 10 days, already higher than typical low Earth orbit exposure. Extend that to months, and the cumulative dose increases significantly. The long-term effects are not fully characterized. The only human data set we have for deep space exposure comes from the Apollo astronauts. 24 individuals who travelled beyond low Earth orbit. A study published in 2016 observed that those astronauts showed a significantly higher rate of cardiovascular disease mortality, around 43%, compared to astronauts who remained in low Earth orbit, where the rate was close to 10%. The sample size is small, too small for definitive conclusions, but it's also the only data we have, and it points in a direction that is difficult to ignore. Then there is lunar dust. Unlike Earth soil, lunar regolith has never been weathered by wind or water. The particles are sharp, jagged, and electrostatically charged. They cling to surfaces, infiltrate seals, and resist removal. During the Apollo missions, astronauts reported what they described as lunar hay fever after brief exposure. Irritated eyes, sore throats, coughing. That was after hours, not months. Now imagine living in that environment. Every time an astronaut exits and re-enters the habitat, some amount of dust comes with them. Over time, it accumulates, it circulates, it becomes part of the air you breathe. On Earth, prolonged exposure to fine particulate matter, especially sharp silica-like particles, can lead to chronic lung diseases like silicosis. We don't yet know if lunar dust will produce similar outcomes over long durations, but the possibility is there. Reduced gravity introduces another set of challenges. The Moon's gravity is about 1/6 of Earth's. Over time, that affects bone density, muscle mass, and cardiovascular function. We have data from astronauts on the International Space Station where microgravity leads to bone loss and muscle atrophy, if not counteracted by rigorous exercise. The Moon's gravity is higher than zero, but lower than anything the human body evolved to operate in. The long-term baseline for human health in that environment is still an open question. Add to that the psychological dimension, isolation, confinement, distance from Earth not measured in hours but in days, communication delays, the knowledge that evacuation is not immediate. On the ISS, a crew can return to Earth in hours if necessary. On the Moon, return is a multi-day process, dependent on launch windows, system readiness and coordination. All of these factors are manageable in isolation, but together, over extended periods, they create a profile of risk that is fundamentally different from anything we've experienced before. And then there is the inevitability that sits at the edge of all of this. It's not something NASA emphasizes, it's not something that appears in mission highlights or public briefings, but it's something that anyone involved in long-duration operations in extreme environments understands. If humans live and work somewhere long enough, someone will die there. Not necessarily in a dramatic failure, not in the explosive way that captures headlines, but in the quiet, ordinary ways that humans die when they are far from comprehensive medical care. A condition that progresses faster than expected, an injury that can't be fully treated with the equipment available, a system failure that intersects with human vulnerability at the wrong moment, or simply time. Because as rotations extend, as people spend longer periods on the Moon, the probability space changes. The environment itself is not forgiving. It does not accommodate mistakes easily. And it does not provide the same margins for recovery that Earth does. The first death on the Moon that is not the result of a catastrophic accident will be a different kind of moment, not a failure of the system, but a confirmation of what the system has become. Because when someone dies in a place, and their remains stay there, not returned, not recovered in the way we would expect on Earth, that place crosses a threshold. The Moon has been visited, it has been studied, it has been photographed, mapped, sampled, but it has never been inhabited in the way that creates continuity across generations. A grave changes that. On the Moon, there is no weather, no wind, no water, no biological activity to break things down. A burial in lunar regolith is, for all practical purposes, permanent. It is a marker that persists not for decades, but for geological timescales. That is not the language of exploration. That is the language of habitation. And that is the moment when the distinction this entire story rests on becomes impossible to ignore. Destinations are places you leave. Homes are places where your story ends. The transition from one to the other is not marked by a flag or a speech or a specific mission number. It emerges from the accumulation of infrastructure, of routines, of people who build their lives around being there rather than getting there. The reactors that keep the base powered through the 14-day lunar night. The habitats that shield crews from radiation and micrometeoroids. The systems that extract water from ice and turn it into air and fuel. The legal frameworks that define how space is used without formally dividing it. All of these pieces taken together are not just supporting exploration, they are enabling permanence, and permanence has a direction. It bends away from departure. So when we say that the next humans to reach the moon will never come back, what we're really saying is this. They will be part of a system that no longer revolves around returning. They will come and go, individually. They will rotate in and out. They will board spacecraft and watch the Earth grow larger in the window as they make their way home. But the presence they are part of will remain. Continuous. Expanding. Indifferent to the idea that it should ever stop. And somewhere along that trajectory, quietly, without announcement, without a clear line in the timeline, the moon will stop being a place we visit. It will become a place we are. Part 12. The moment the moon stops being a destination. Let's go back to the Pacific Ocean. April 10th, 2026, 4 days ago. The capsule is still drifting in the aftermath of descent, rocking gently on a surface that looks almost too calm to belong to anything that just survived something so violent. The parachutes have gone slack now, collapsed into the water like discarded skin after a performance that pushed every system to its edge. They trail behind Orion in uneven drifting arcs, slowly pulled outward by ocean currents that feel almost indifferent compared to what just happened above them. Around the capsule, recovery teams are already working with practiced precision. Small boats circle it in tight controlled patterns, while divers enter the water to secure the spacecraft and begin immediate inspections. Above them, a helicopter hovers low enough that its rotor wash flattens the ocean into rippling circles, as though the surface itself is being pressed into submission. Cameras hang beneath it, broadcasting everything live across the world, turning a technical recovery into a global moment of collective attention. Inside the capsule, 4 astronauts are still adjusting to the return of gravity and atmosphere, processing the fact that the journey is actually over. When the hatch opens, they emerge into sunlight that feels almost too bright after days of controlled darkness and deep space silence. They move carefully, not because they are injured, but because their bodies are recalibrating to a world that suddenly feels heavier and louder than the one they just left behind. One by one they step out, they wave, they smile, and they are guided onto the recovery vessel, where stable ground replaces the motion of the ocean for the first time in 10 days. The moment stretches longer than expected, not because anything dramatic is happening, but because everyone involved understands what it represents. Navy crews applaud. NASA engineers watch quietly, many of them holding expressions that mix relief with disbelief. Somewhere in the background, a sense of release moves through the entire scene, as though a collective breath that began at launch is finally being let out. At first glance, it looks like an ending. Every familiar cultural signal tells you this is the final frame. The mission launched, it succeeded, the crew returned. The story closes itself in a clean, satisfying loop that feels complete in the way human narratives are supposed to feel complete. But that interpretation only works if you stop the story here. Because while those astronauts were standing on the deck of that recovery ship, shaking hands and adjusting to gravity, something else was already in motion thousands of miles away. Inside the vehicle assembly building at Kennedy Space Center, the next rocket was already being stacked. Not in a symbolic sense, and not as a distant plan waiting for approval, but as an active physical process already underway. Segments were arriving. Integration work had begun. Systems checks were running in parallel with the analysis of the very mission that had just ended, as if the two events were part of a continuous chain rather than separate milestones. This is where the illusion of return begins to break down. What looks like an ending on the ocean is actually just one validation point inside a system that never fully stops moving forward. Artemis is not structured like Apollo, where each mission stood alone as a complete story. It is structured like infrastructure, where every success immediately becomes input for the next stage, and every return is simply proof that the chain has not broken yet. The splashdown on April 10th is not a conclusion in that system. It is a checkpoint, a confirmation that the hardware, the trajectory, and the human endurance required for deep space travel all functioned under real conditions. But in engineering terms, confirmation is never the end goal. Confirmation is permission to scale, and scaling is already happening. The heat shield that survived re-entry is now part of an ongoing investigation into how materials behave at temperatures approaching 5,000 degrees Fahrenheit. The European-built service module that carried the crew across more than 250,000 miles is being analysed not as a finished success, but as a component that must be refined for longer, harsher missions. Even systems that performed flawlessly are being re-evaluated, because good enough to return is not the same as good enough for permanent presence. This is the subtle but crucial shift that defines everything after Artemis 2. The program is no longer asking whether it can reach the moon and return. That question has already been answered. The new question is whether it can build something that does not require full reset between arrivals, because that is what permanence actually means. It is not about distance or duration. It is about continuity. It is about whether the system still exists when the humans temporarily leave it. And that is where everything begins to point in the same direction. The Artemis roadmap is not a series of isolated missions. It is a staged construction plan for a continuous human presence beyond Earth. Artemis 3 is not being designed as a simple landing. It is being designed as a systems rehearsal, where astronauts interact with landers, suits, and life support systems in integrated conditions before those systems are permanently deployed. Artemis 4 is expected to mark the first true return to the lunar surface in over 50 years, targeting regions near the South Pole where sunlight and ice deposits overlap in ways that make sustained presence physically possible. Artemis 5 and the missions that follow begin shifting the role of astronauts again. They are no longer just explorers testing unknown environments. They become operators of a growing system. They activate pre-positioned cargo. They repair infrastructure that was already deployed before they arrived. They verify that robotic systems and automated construction efforts have done their job correctly. In other words, they arrive not to discover the moon, but to maintain what is already being built on it. That is the point where the language starts to lag behind reality. Officially, this is still described as exploration, but operationally, it is becoming something else entirely. Power systems are being planned for deployment on the lunar surface, including nuclear reactors designed to survive the 2-week lunar night when solar energy disappears completely. Communication relays are being positioned to maintain constant contact between Earth and the far side of the moon. Cargo missions under the CLPS program are already delivering precursor systems that will eventually form the backbone of a permanent outpost, and permanence changes everything it touches. Once you introduce infrastructure that does not leave, you also introduce the need for humans who do not simply visit, but rotate. That distinction matters more than it initially appears. A mission has a departure, a rotation has a replacement. One ends, the other continues. Over time, that structure produces a new category of human experience. The first crews will still be astronauts in the traditional sense, selected by agencies, trained for years, and sent on defined missions with clear endpoints. But as systems mature, that profile begins to shift. Engineers become specialists assigned to specific lunar systems. Scientists begin working extended rotations focused on geology, resource extraction, or environmental monitoring. Medical personnel adapt protocols for long-duration exposure to reduce gravity and elevated radiation. Eventually, the distinction between visiting and living begins to blur. At that point, the moon stops being a destination in any meaningful sense. It becomes a workplace, a habitat, a place where routines develop, where responsibilities accumulate, and where time is measured not by missions completed, but by cycles maintained. And once that shift happens, something else follows quietly behind it. The idea of coming back stops being central to the experience, not because return becomes impossible, but because return becomes incidental, a logistical step, not the purpose of the journey. This is where the deeper meaning of April 10th begins to emerge. The astronauts who splashed down did not conclude a story. They validated the beginning of a system that is designed to continue without them. Their return proves that the chain holds. And because the chain holds, it will extend further. From the ocean, everything looks like an ending. From inside the program, everything is already continuation. And somewhere ahead, beyond the missions we can currently name, beyond the hardware we have already built, the first human will step onto a moon that is no longer waiting to be explored. They will arrive into something already active, already powered, already inhabited in cycles of presence and absence that never fully reset. And at that point, coming back will not disappear. It will simply stop being the defining part of the story.